All right, ladies and gentlemen, this is going to be review video 19, ideal gases and gas properties. So ideal gases are something that you would have heard of already if you took baby chem. But in terms of what is an ideal gas, first and foremost, ideal gases are not real. They are very fake. However, they do have their uses when we're trying to do calculations and we're trying to figure out properties of gases. And what they really are is a hypothetical gas that is going to obey the gas laws exactly and not act weird at all, right? And that's how we know that they're fake, because everything acts a little weird sometimes. Everything is going to break rules, but ideal gases are not going to break rules. But again, we know that that's not real. So why is it that we cannot deal with real gases in this class? And the answer is quite simply because the math starts to suck. When you stop making assumptions and when you stop believing that your gases are following rules, the math gets terrible. So this over here, this fun little thing, is just the beginning of the type of math you would have to start doing when you stop assuming all of the things that we're about to assume about ideal gases. And while some of you may be brave enough to try math like that, two things. One, it's above the scope of this class, and I didn't start doing math like this until my master's program. And two, it's just a lot. And so we don't have time to focus on math like that. All right, so here's going to be our list of assumptions that we're going to make sure that our math is as easy as physically possible. Assumption number 1, gas particles have no volume. Obviously, gas particles do in fact have volume. However, they're small, gas particles are little, and there's going to be a ton of space between them, so we can safely ignore the volume of our gas particles. Not the volume of the gas sample entirely, but just the volume of the tiny little gas particles within a sample. Assumption number 2, gas particles move in straight lines and their collisions are perfectly elastic. Basically, it just means that gases aren't going to zigzag all over the place, and when they collide with something like each other or the wall of the container that they're in, none of that collision force is going to be lost through friction or drag or anything weird. It is, but we're going to ignore that. Assumption number 3, gas particles exert no attractive forces on each other. They absolutely do exert attractive forces on each other, but because those gas particles are so small and because they're so far apart and because they're moving as fast as they are, we're going to go ahead and ignore those attractive forces that they exert on each other. And then finally, our 4th assumption is that our average kinetic energy is directly proportional to temperature, which it mostly is, and those are pretty much almost the same thing, but it's not perfect, and so the difference between those two things is so small that we're just going to pretend it doesn't exist. All right? And all of those assumptions are going to make our math very nice. Properties of gases that we need to pay attention to, these should not be new pieces of information for you. Pressure is defined as how much force a gas is going to exert on the container that it's in, right? Because if you force a gas into a really small container, it's probably going to be under really high pressure. But if you put a gas in a really big container, there's probably a lot less pressure there. There are a ton of different pressure units, and all of them are going to be acceptable to use in the different gas laws that you're going to see in the next video. But the catch is that whatever your pressure units are, they need to match each other if there's more than one pressure value in your equation, and some constant values require specific pressure units. So I'll teach you how to identify that. The first one is atmospheres, which you're going to see the most often abbreviated ATM. Then there's kilopascals, abbreviated kPa. Millimeters of mercury is going to be abbreviated mmHg. Pounds per square inch is abbreviated PSI. And finally, there's an odd one every now and again you'll see as torr, and its abbreviation is still torr. But that one I would say is the most rare overall. To convert between pressure units, because again, shockingly, you're going to have to do conversions in this class, here are the conversion factors. 1 atmosphere of pressure is equal to 101.3 kilopascals of pressure, which is equal to 760 milliliters of mercury, which is equal to 760 torr, which is equal to 14.7 psi. All of those numbers equal all of those other numbers. That is the exact same amount of pressure written 5 different ways. And you're going to use those equivalencies to convert between them in dimensional analysis fashion. So if I had to convert 3.06 atmospheres to millimeters of mercury, I would just set up a normal dimensional analysis. 3.06 ATM. I want to get rid of ATM, so it's going to go on the bottom. I want millimeters of mercury on the top. And I literally am going to take the two numbers from my equivalency, in this case 1 and 760, and sub it in. When I do my math, I'm going to take 3.06 and I'm going to multiply it by 760, and that is going to give me 2,325.6. Now, obviously, I'm going to round that for sig figs, and 3.06 has 3 sig figs, so I'm actually going to round that off to 2,330. All right, and that's going to be my answer. If I wanted to convert 56 torr to kilopascals, I start with 56 torr. I do my dimensional analysis. Torr goes on the bottom. Kilopascals goes on the top. And again, I'm going to go back up to my equivalencies, and I'm going to take the number for kilopascals and take the number for torr and put it straight in my dimensional analysis. So 760 torr, 101.3 kilopascals. I take my calculator and I multiply and divide that out. And that is going to give me 7.5 kilopascals. Now, one thing that I always see people doing that is incorrect is people think that if I'm in atmospheres, I have to convert to kilopascals, to convert to millimeters of mercury, to convert to torr, but you do not have to do that. You can literally go straight from atmospheres to torr because every single one of these numbers equals every single one of those numbers. You do not have to do a 5-step calculation to get from one to another, and that's the most common error that I see. All right, enough about pressure. Let's talk about volume. Volume is going to be how much space a gas is going to occupy. The thing about volume is that 9 times out of 10, it's going to have to be in liters, so you may as well just convert to liters right off the bat. The most common conversion that you'll have to do would be milliliters to liters, and in terms of how to do that, you're just going to divide by 1,000 to get there. But again, you're welcome to always set up your dimensional analysis if you're not sure what number to divide or multiply by. Temperature is our next pressure property. Temperature is going to be defined as pretty much the average kinetic energy of the gas. That temperature, 9 times out of 10, is going to have to be in Kelvin. So if you have to convert from Celsius to Kelvin, all you have to do is take your Celsius number and you're going to add 273.15 to it. So 0 degrees Celsius in Kelvin would be 273.15, because all I have to do is add that number to get to Kelvin. All right, if it was 1 degree Celsius and you added 273.15, you would end up with 274.15. So literally you're just adding that value to get from one to the other. Next property I want to discuss is moles. Moles, in terms of gas laws, is always going to be abbreviated with the letter N. Do not ask me why the letter N was picked, it just was. But that is defined as how much of the gas is present, not in mass, but in moles, and you should be familiar with moles at this point. If you are given mass, you are going to have to convert it into moles to use the gas law formulas, because there is one particular formula that has moles in it directly, but a couple of the other ones will use it a little bit peripherally. Last thing isn't really a property, but it is something you need to be aware of, and those are the R values. R values are constant values that scientists came up with a long time ago, and they are used most often in conjunction with the ideal gas law, which you'll learn about in the next video, which is PV equals nRT, and you can see that R constant value straight in there. There's a lot of options for R values, and these four are the ones you'll see the most in this class. We have 0.08206, which is one option. We have 8.314, and you're seeing that number pop up twice. And then we have 62.36. But I want to point something out about their units real quick. The units of most of these are pretty similar. Like I'm seeing Kelvin to the negative first in all of these. I'm seeing moles to the negative first in all of these. But what's absolutely, absolutely different between them is this, the pressure bit. Technically, joules isn't pressure, it's energy, but that is the difference between these R values. So if you're trying to pick the correct R to use, all you have to do is look at the pressure unit in your problem. Whatever pressure is given as millimeters of mercury, kilopascals, atmospheres, you just have to match it to one of these R values. So if my pressure is in atmospheres in my problem, I should be using this R because this R has atmospheres in its unit. If my pressure is given to me in millimeters of mercury, then I should be using this R because it has millimeters of mercury in it as a unit. So when it comes time to do those gas laws and use those things, I will point this out again, but that's how you're going to pick the appropriate R value. If you're not sure about any of this, please ask me in class.